Hello, I, Dr. Minal Nerkar, welcome you all to this session on binary search algorithm using recursive method. In this video, we are going to learn how to implement the recursive binary search, its analysis, and the comparison between the linear search and the binary search. In previous lecture, we studied what is binary search, how it works, iterative binary search implementation, its analysis. It uses divide and conquer strategy and input needs to be sorted one. So today we will see the recursive binary search implementation where the function calls itself with a smaller search space. So first we will calculate in the binary search the function is it is returning the integer value, so that is nothing but the as we are returning the index of the match found, so it is a return value, then the name of the function and the parameters passed to the function. So first thing is nothing but the sorted array. X is nothing but the element to be searched. Low and high represents the lower bound and the upper bound of the array. First, we will check if high is greater than or equal to low. This means if there are some elements in the array or not. If yes, then we calculate the mid of the index using the formula low plus high minus low divided by 2. So next we will compare the element to be searched, that is x, with the array mid. If, as I told in previous lecture, it has three possibilities: either the elements are equal, less, or greater. So if elements are equal, we are returning the index of the mid. If the element to be searched is greater than that of the mid element, then we will focus our search to the right side of the sub array, right half part of the sub array. So we need to update the lower bound of the sub array. Okay, so we are giving call we are recursively giving call to the binary search, okay, with the parameter array element to be searched, and the lower bound is now becoming mid plus 1 and upper bound remains as it is. Okay, else if both the conditions are false, then control will go to this binary search call. So if x is less than that of the array of mid, then we recursively search the left half by calling the function with the parameter low to mid minus 1. Okay, so over here we are updating the upper bound. In this case we have updated the lower bound of the array. So if low becomes greater than that of the high, it means the element is not present, so we return minus 1. So this is how it works. Minus 1 is written if the element is not present, and if the element is present, it returns the index where we found the first match. Now coming to the analysis part, over here the first call will have the total number of elements as n. So in the first iteration, the length of the array is n, whereas in the second iteration, it is reduced to half because we are finding out the mid and comparing that mid with the element to be searched. And accordingly, we will decide whether we have to focus our search to the left half part or the right half part. Okay, so now in the next iteration, the size of the array will reduce to the half of the previous size. So now the new size for the third iteration will be n divided by 4, that is nothing but n upon 2 raised to 2. Likewise, if we go after certain number of iteration, we got the size of the array as 1. So consider that ki after the kth iteration, we are getting the size of the sub array as 1. So over here, the length of the array is equal to n divided by 2 raised to k. As we know that at after the kth iteration, the size becomes 1. So n divided by 2 raised to k will be equal to 1. This can be represented as n is equal to 2 raised to k. Now we will apply the log function to both the sides of this equation. So now this equation will become log to the base 2 of n, which is equal to log to the base 2 of 2 raised to k. Now this can be rewritten as log to the base 2 of n, which is equal to k log to the base 2 of 2. And as all of you know that this term is equal to 1. So what we will get over here is k is equal to log to the base 2 of n. Hence, the time complexity of the binary search is coming out to be log to the base 2 of n. This is for the binary search, as we are dividing the given array into two equal parts. Now, if we want to split the given array into three parts, that is, if we want to run the ternary search or tertiary search, then in that particular case, the time complexity is coming out to be log to the base 3 of n. This will be the time complexity of the tertiary search. Okay. Now, moving to the next slide, the best case, worst case, and average case time complexity of the algorithm. So, as in every recursive call, the search space is divided into two parts. Therefore, the number of elements to be searched is reduced to exactly half in every step. So, in best case, the element is found at the middle position during the first comparison itself. So, the time complexity is coming out to be big O of 1. In average case, the time complexity will be big O of log n. How log n, that we have seen in the previous slide. Now in the worst case, the algorithm continues recursively until the search range becomes empty. Therefore, the time complexity is big O of log n. The space complexity is big O of log n because each recursive call is stored in the call stack. So, to summarize, the recursive binary search is an efficient searching technique that works on sorted array. It repeatedly divides the search space into two parts and calls itself recursively on appropriate half part. Thus, it has a time and the space complexity of big O of log n. Thank you for watching.